Okay, and this is a joint work with Gil Kur from MIT and Ohad Shamir from Weizmann. In this paper, we show that we need memory which is quadratic in the dimension for some learning streaming problems. So the first problem is linear separation. And here you get pairs xi, yi. These pairs are separated with some small margin. And the goal in the end is to find a hyperplane which classifies most of the points correctly. And the second is linear regression, where you get a stream of dissatisfiable equations. And your goal is to find a vector w hat, which is an approximate solution to this set of equations. And both require D-square memory, as we show. I just want to say that the examples come in a streaming order, like the order can be adversarial. So let's compare this to the perceptron algorithm. So the perceptron has linear memory, but it has like good guarantees, but the guarantee of the perceptron is on the online mistake loss. And we show that if we are interested in outputting a final hypothesis, which is good on the data, then actually we cannot do it with linear memory. We'll need the memory of d squared to do it. So I just want to mention that there are related works, and one very nice work that was presented this week is by Sharan, Sidford, and Valiant, where they show memory sample trade-offs for linear regression in a setting which is slightly different than ours. Okay, so how are we going to show these lower bounds? So we reduce to another problem, which we call the approximately null vector problem. So in this problem, you get d-1 unit vectors. And the goal is to find a vector which is approximately orthogonal to all of them. And we show that doing this requires a memory of d squared. And then by reduction, we show that both the prediction and the regression problem require at least this same amount of memory. So first, we show that linear regression is harder than finding an orthogonal vector. And in order to do this, we show that we can solve the orthogonal vector problem using an algorithm for linear regression with the same amount of memory. So what we do, given input to the orthogonal vector problem, we just create a an equation system that its solution is the orthogonal vector. And then we can just simulate the algorithm for linear regression and output its solution. And here we show that linear regression can only be harder than finding an orthogonal vector. And the same, and now we'll show that linear separation is also harder than finding an orthogonal vector. And again, so we are getting some inputs to the orthogonal vector problem, and we'll show how to create a data set such that any separator will be an orthogonal vector problem. It will be an orthogonal vector. So I won't get into the technical details, but again, this shows that linear separation is at least as hard as finding an orthogonal vector. So now let's discuss on how we show that finding an orthogonal vector requires the memory of d squared. So what we show that after receiving d over 2 vectors, any successful algorithm has to roughly remember their span. And if it doesn't have enough memory, then it's going to confuse between many vector spaces which are further apart. And in this case, we show that the algorithm is going to have a lot of error. And in order to remember a vector space of dimension d over 2, which is a subspace of Rd, we need d squared memory. Okay, so I just want to say that the results in this paper are tight. So for linear separation, it is true that if the margin is gamma, then with a memory of 1 over gamma to the 4th, it is possible to find and approximate separator using random projections and subsampling. And our lower bound show that actually this cannot be improved. And also for linear regression, so we show that with little o of d squared memory, it's impossible to solve the set of equations. But if you have d squared memory, you can obviously store the whole set of equations and solve the problem. That's it. Yeah, so we've been trying to prove it for multipath. We didn't manage yet, but we're now thinking of different methods to extend it to multipath. Yeah. And this will imply also bounds for optimization if we get the right. Yeah.